Now we are going to look at regression, a most popular use case in any data science or analytics firm that is typically useful for prediction as well as explanation, right? And in examining this use case, we'll start with basic regression framework. Let us talk about regression, the most popular and common use case in analytics as well as data science, right? So here we are going to talk about basic framework of regression analysis and the core concepts of computational mathematics involved in regression. I understand you have not yet studied regression analysis, but I believe you have been introduced to ordinary least squares as a technique. So we are going to see how ordinary least squares is a useful tool in estimating a regression model and what does it essentially involve, right? So regression as a use case, we are going to think from a practical use case that we will commonly encounter, we typically encounter in any marketing analytics problem. So it is about predicting your volumes given certain marketing spends that you do or certain changes in prices that you bring about, right? How would you approach this problem in the form of an analytics solution, right? So our interest is predicting the volumes given change in the price, right? So our interest is in understanding for what is the incremental impact that's going to be for a certain change in price. And the predictions are required for volumes, and these are typically further used to assess several price changes and thereafter take a certain pricing action actually in the market. So should I do 5% or 10% or 15% price increase? If I do that, what is the change in volumes that's going to occur is what I'm interested in. And this is something that you would use a regression model for to build the predictions first. And based on the predictions, the firm will decide whether to go ahead with 5% or 10% price change, right? And in regression, we are typically talking about a linear model. So what is of interest is what is the change in volume that will occur if the price is lowered. And this relationship is, let's say, modeled as a linear relationship. So the relationship is fitted typically with X variable as price and volume as your Y variable, something that you would study as a regression framework with X and Y in the form of a mathematical model, right? So as I say, linear relationship, it is represented by a line, right? So why do we fit a line and how do we fit a line, right? Let me take you to the experiment that we have all been familiar with in our 11th or 12th standard physics laboratory, right? The experiment is called Ohm's law, where we studied relationship between the voltage and the current flowing through the circuit, right? So what is it that we did there as part of the experiment? We changed the value of the voltage and measured the corresponding current values that were flowing through the same circuit, right? As part of the experiment design further, we did a plot of voltage and corresponding current values on an X and Y axis, right? So what we had on X axis was values of different voltages applied, and on Y axis was different currents these voltages actually produced through the circuit, right? And then we fitted a line. We fitted a line in such a way that many of the points that you can see on the graph are actually passing through this same line, right? So that is the same principle that is applied when we estimate a linear relationship through a regression, right? How do we do it more scientifically? I want to fit a line in such a way that it passes, most of the points basically are passing through that line. The second idea is if some of the points are not passing on that line, they are not there on that line, then the distance of those points with respect to that line is something that is minimum, right? So this is where the idea of ordinary least squares or sum of square errors specifically comes in, right? I want to minimize the error between the predicted values and the measured values. Predicted values are the values that you get from the model, right? And this error difference minimization is what is written as an objective function in the form of sum of square errors, right? So this is the main concept of sum of squares. And let's take a look at ordinary least squares that has been introduced to you, right? So a regression model which is in the form of a line is what I can write it as y equal to x beta plus epsilon. And I'm now going to write what is the residual sum of square that must be minimized, right? So this error square is actually equal to y minus x beta multiplied by y minus x beta, because I can rephrase the same equation y equal to x beta plus epsilon to be epsilon equal to y minus x beta, right? So I'm interested in minimizing this matrix product y minus x beta transpose y minus x beta, right? And this is minimization carried out by changing the values of beta, right? So beta is what determines the intercept and the slope of a line, right? So how do we come up with choice of betas that minimizes the sum of squares, right? So again, going back to our 12th standard concepts of derivatives, right? So how do we get to the optimal values of beta such that I have a minimum sum of squares? So we understand a particular function, when it is at minimum, its derivative is equal to 0, right? So I will write derivative of residual sum of squares with respect to beta and equate it to 0, which is what you see as an equation x transpose y minus x beta is equal to 0. The product of two matrices x transpose and y minus x beta equal to 0, right? So how do I obtain beta from this equation? After doing a little bit of algebraic rearrangement, I can straight away see I have beta is equal to x prime x inverse x prime y. And this is what we call as ordinary least squares estimator. It is obtained by x transpose x inverse x transpose y. Now you have to tell me where exactly this will fail. What I have here is data which is available to me as x and y matrices, and it will work as long as x transpose x inverse exists. So let us apply these concepts in an actual problem setting. Let's try to go through an R program where I essentially do the same thing and estimate the regression model for you.